Starting today, yeah, mechanics and materials is in here right afterwards, so you don't have to go somewhere else. So if you missed that, now you know. Okay, so today we're diving in. Notes are starting today. I'll probably assign a homework today. I gotta see. We'll see. I gotta look at next week's notes to see how quick or how far we'll get and whatnot. But if anything, there'll be abbreviated homework assignments. The other thing I forgot to mention, I did send out an email. Hopefully, you guys get those emails. There's just like a standard list that they give us that we email to, but I do use skeleton notes in here. So if you can, and I posted all the skeleton notes for the whole semester. So if you get a chance, try to print these things out. You'll see as I go. I do not have the best handwriting, and so I try to like put together, and I'll try to type when we get into like lots of notes. I'll try to type it in here so you can see it, but. For the most part, it's not too bad. You'll learn how to read my handwriting by the end, I think, and I've improved it quite a bit. And the other thing I want to note too is when we get into some example problems, you'll see that maybe I don't have the best handwriting, but my answers are very, very clear and concise, and I want you to aim for that by the end, okay? So what we're going to do today is just kind of go over like just the introduction to dynamics, what it is we're going to cover, the structure of the course, and then we're going to dive into particle dynamics, and in fact we're just going to do 1D particle dynamics, which then will lead us into 2D, and we'll go from there. So and then somewhere around 40 after, the TAs are supposed to come in, and so they're going to introduce themselves and kind of talk to you about how the recitation session is going to be laid out, and you'll put a name to the face, and then or a face to the name, and then anyways they're going to go over that. So right around 140. On a usual Friday, we're going to try to watch a lot of YouTube, okay? Watch some, like, YouTube Fridays. It started out being, like, engineering Fridays, and then over the years, it's turned into YouTube. We just watch YouTube. But they're all typically mostly related to the topics at hand, right? We just haven't had a topic yet, so I don't have a good video to show you right now. So with that being said, any general questions? I'm going to try to post. I got this one recording. I did not record. I recorded the first 10 minutes of the last class, and then this thing shut off because I wasn't actually touching it. But from now on, it should be recording. I should post it on YouTube, and we should be able to go from there. So, and it's a good resource to have. If for some reason you can't make it to class, or you want to go back and revisit a topic, you can do that. So, and I teach with the iPad, so it's actually a pretty clean way of doing it. When I first started, this is back to me being older than I thought that or older than I think I was, or I am, is that when I started teaching, whenever we wanted to bring in like a printout or something like that, we used a projector, like I don't even know what they're called, but it's like a light bulb in a mirror. You guys ever see these? I don't know, what are those things called? It is an overhead projector. Yeah, right. And so it's like a little thing, and then it's a clear, and then it projects it up, and it hits the mirror, and then it goes back to the thing. That's how I started teaching, and then I have actually taught on a chalkboard once. I don't even think they're on campus anymore, but they used to be. But I'm still young, just like you guys. All right. So let's get started. So introduction to dynamics. We talked about this briefly last time. Statics. We had the sum of the forces were equal to 0. Sum of the moments is equal to 0, right? And our problems, when we solved these problems, or when you solve these problems in statics, you start out with a free body diagram. You drew a free body diagram. You put all the forces and moments on it, and then you just said, oh, all these things have to be equal to 0. Same process. It's the same. I think it's the same book that you guys are using, right? You had Bedford and Fowler statics, and now we're doing Bedford and Fowler dynamics. So all that, they're very much related to each other. The process for solving the problems are very related to each other, okay? But in this case, statics, sum of the forces equal to 0, sum of the moments equal to 0. Dynamics, sum of the forces is equal to mass times acceleration. We'll get into that. I mean, that's Newton's second law right there. And then all we're going to say for the moments, some of the moments do not equal 0. Right? And in fact, like I said, this is going to be the biggest equation you probably used to date in your careers, is that moment equation. For 3D rigid bodies, it just blows up. It's called these Euler moment equations. They're very large. So how are we structuring the course? Okay. One thing that I try to do in this class, it is a difficult topic, so I try to make it as structured as possible. A very clear, concise path forward, okay? So the first thing we're going to cover, very procedural the way we do it, is I mentioned this before, we're going to cover particles, okay? In particles, mass is concentrated at a point, okay? Similar to what was done in physics, right? You did cover some dynamics in physics, projectile motion. Projectile motion is something covered in your basic physics. We start out with projectile motion stuff. We quickly kind of go away from that, but we do start out with that, okay? The second topic we're going to cover is 2D rigid body motion. And the third thing we talk about is 3D rigid body motion. Okay. The stuff that we learn for particles, we then, a lot of those topics we then carry on to 2D rigid bodies. And then what we learn about 2D rigid bodies, we carry that on into 3D rigid bodies. So that's the structure of it. In particles, we have two quizzes in particles. We have 2 quizzes in 2D rigid body dynamics, and we have and then we have the final on 3D rigid body stuff. Okay, that makes up all of our quizzes. So then for each one of these things, I guess let's talk a little bit about these really quick. The rigid body motion. What did I do here? For these things, we have both of those. We have distributed mass. What's going on here? What are you doing? Wait. It's been a while since I've operated my iPad. Oh. Right, the mass is distributed. And the body is non-deformable. I just made that word up, it looks like. Okay, but you can't deform the body. See, in mechanics and materials, what you're learning about now is if you apply a force, or what you will learn about, if you apply a force to an object, that object will deform, right? In our world, in dynamics right now, if you apply a force to a body, they don't deform, okay? Will they really deform? Yeah, they'll deform a little bit, but that's a little more advanced. That's like a grad level course when we have to consider something moving and deforming. Mechanics and materials, they're just deforming, but not flying through the air. In dynamics, they're not deforming, but are flying through the air. So we'll get that. Okay, so we're going to do those things. For each one of these, so that's kind of the structure overall. That's the topics that we're going to cover. Okay, for each one of these things, we're going to follow the same path. The first thing we're going to do is we're going to do kinematics, which is the geometry of motion. Okay. We're going to study geometry of motion first for each one of those things. Then we're going to do kinetics, which is forces resulting in motion. Right? We're going to solve kinetic problems, we're going to do 3 methods. We're going to do force, mass, acceleration. Then we're going to do work energy. And then we're going to finish up with impulse momentum. Right? So that's the path for each one of those things. So just got to clarify, so we're going to do particles. First thing in particles, we're going to do particle kinematics. Once we get through particle kinematics, then we'll do particle kinetics. And then we'll start out with force, mass, acceleration, work energy, impulse, momentum. Then we'll go on to 2D rigid bodies, do the same thing, kinematics, kinetics, FMA, work energy, impulse, momentum. And then we do 3D rigid body, do kinematics, kinetics, FMA, and actually we stop right there. We don't make it through the rest of them, but just kind of feel like that's the process we're going to be following. Okay, pretty straightforward class. There's a lot of stuff in there, but at least the path is clear. I honestly think that the first part of the class is the most difficult because there's integrals. We do a lot of integrals and stuff at the beginning. You guys might hate integrals. I hate freaking integrals. Okay? We start out with some integrals, and then there's a lot of like feeling, like how do we go about solving this problem? It's not as clear of a process. Once we get into 2D rigid body and 3D rigid body stuff, it is very procedural. No more integrals, and we just go, this is how you solve these problems. Free body diagram, write your equations of motion, solve the problem. Very straightforward. I mean, obviously there's lots of things to get hung up in there, but it does follow the same process each time. Is Mickey here today? Mickey? Mickey's not here today. Or Mickey said this is the third time he's taking the class. Fourth time he's taking the class. He's not here today. I was going to ask him what his opinion was, but he's not here today. Okay. All right. So like I said, we're starting out with particles. So our first topic here is going to be particles, and then we talk about kinematics. Again, kinematics is the geometry of motion. So also, by the way, I just take the stuff I'm lecturing here. I literally just took straight out of your textbook. Okay, when I first made these notes years ago, I just opened up the textbook and just started walking through the textbook and said, "Hey, what's the important stuff that I'm going to be pulling out here?" I use the same wording, the same variables and everything as the book. So you can just open it if you don't understand something. Like I said before, open up the book and go through the book, and they'll kind of cover these things in a little more detail. Their drawings will be a little bit better and stuff like that. So, geometry of motion for kinematics. Again, this stuff is going to be review, and you're going to be like, I don't need to worry about this stuff. It quickly diverges away from like what you've done in physics. So, what we got right here. The book starts out as like, oh, here's a path that a particle is traveling along, right? So this particle starts out here and it moves over to here. It's traveling along that path like that, okay? When we deal with these problems, we have to define an origin and a coordinate system. What are we saying is the 0 point, and what is our coordinate system going to be? For a lot of these examples, we're just going to use Cartesian coordinates, right? But real quickly, I think by Wednesday next week, we're going to do polar coordinates and this thing called normal tangent coordinates. We're going to have a couple different coordinate systems as we move along. But for this, we start out with just a Cartesian coordinate system with an origin state there. When we define the position of an object, there's a position of it. And the book calls that R. I always think it's pretty funny when they choose certain variables, right? They use the letter R because of all the R's in the word position, right? It's one of my favorite jokes. I'll use it a lot. And if you don't laugh, that's okay. As long as I think it's funny, that's all that matters, right? I will use that joke a lot. But yeah, because we do it a lot, right? So R stands for position in the book, okay? That's a vector. It's from the origin, and it points to the particle, right? And then after a certain amount of time, that particle has changed location, and that position would be R of t plus delta t. Right? A short time later, delta t has passed. Okay, it's moved along that path, and then there's a vector that goes between the two. That vector is called delta r. Delta r. And that is defined as R of t plus delta t minus R of t. And I'm usually pretty consistent about the bar over top. The bar just means that that's a vector, right? So the book might do it not with bars. It might do it with bold text. I don't quite remember right now, but in our notes, we're going to be I'm very consistent on calling a vector. I put a bar over the top. It means it has like an X, a Y, and a Z component associated with it. So we've now defined position and position after a certain amount of time, and we defined this delta R. How is R changed? It's that vector that points between them, and it's just this vector minus this vector. So there's a little bit of vector math in there, okay? So when we define velocity, right, if we want to say how fast is that particle traveling, right, and this goes back to the definition of derivative. So the velocity v of t is equal to the limit as delta t goes to 0, delta r over delta t. And that is That's how we've defined it before. How is the position change? That's what velocity is. How is position changing with respect to time, right? It's the limit of delta r over delta t, and as delta t goes to 0. So if you look at this, right, this is a big step. That's a big time step. But if we looked at its shorter time step over here, right, then as that delta t approaches 0, is when you get your velocity, right? That's kind of like the average velocity over a large period of time. If that delta t gets smaller, this thing just starts approaching the tangent there, right? And this is a classic definition of a derivative. So this is just equal to dr dt. And another way to write that as shorthand is r dot. Put a little dot on top of it. There's a shorthand for saying I'm taking the time derivative of r, right? That's velocity, okay? Little side note, we're gonna a little side note over on the side. There's just mechanics notation for you. Note, the dot denotes a time derivative. And then a prime denotes a space derivative. You'll see that in mechanics materials. Maybe you've run into that in your career so far. If you see like a dot on top of something, it means you're taking the derivative with respect to time. If you see a prime, it means you're taking a derivative with respect to space. And by what I mean by space, I mean like x, y, or z. Yeah.
Is there any reason you started out with like the magnitude of velocity but ended up with the position vector?
Hold on, what? Sorry.
In your definition of velocity, you just have the magnitude and not the vector. So how do you end up with the derivative of a vector?
The magnitude. Oh, I just added it.
Oh, okay.
Yeah, I just added it, sorry. Right when you said that, I was like, oh, I forgot that, and I put it in. Yep. Yeah, I meant to say that should have been the R right there. That right here is where I was missing it before?
Okay.
Yep.
And would velocity also be a vector?
Oh, yeah, velocity also is a vector. Like, I remember I just said I was very consistent. Turns out I'm not. Call me out when I do that, right? Because this is, right, mechanics is about, like, I'm going to be very clear. I'm going to be as concise as possible, and then we want that. We don't want to make mistakes like that. So yeah, that velocity is also a vector. Okay, and so where you're going to see this, if you run into the prime shorthand derivatives yet, you're going to do it. Like I said, mechanics and materials, in particular, a place that it stands out is there's a beam bending equation. You'll get to it at some point, and then when you get to it, think of me. It's EI. U prime, 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 prime. 4 primes is equal to negative W of X. You're going to get there. It's weeks in advance, but you'll do that, and then you'll see all those primes because it's taking derivatives with respect to X as opposed to taking derivatives with respect to time. So it's very common in mechanics, especially as we move forward. You're going to do lots of mechanics in your career, and then this is a very standard denotation there. The other denotation is positive is tension and negative is compression. You're going to get into that at some point too. There's like certain rules that you follow as you do these things. Okay, so that is the velocity. Then I guess one more comment to make. Velocity is tangent to the path. If not, it's not on the path. It's just deep right there. Velocity is tangent to the path. If it's not tangent to the path, then it can't be on the path, right? So this is deep. This is deep thoughts for today. But you can see up here, as that delta t gets smaller, then this thing, gets closer and closer to tangent. And at that very instant, you're going to be calculating velocities at the specific instances, and it will be tangent to that path. If it's not tangent to that path, then it's not on the path. Okay, and so that's just and you've covered that in physics before too. Okay, acceleration. Those are velocities and positions, velocities, accelerations are key to this class. It's all about that, okay? Acceleration is a function of time. It's just going to be the derivative of velocity. How is the velocity changing with respect to time? dv dt, which can also be denoted as the velocity. Oh, that's a vector, yep. In shorthand, that's going to be v dot, or it could also be the position double dot. Is another way to look at it. The second derivative of the position is the acceleration, and the derivative of the velocity is the acceleration. Okay, so again, that's review for you. You've seen all that stuff before. That's high school physics even. Okay. All right. The next thing the book starts out defining velocity and acceleration, then it dives into this idea of frame of reference and coordinate systems. It's important to understand the difference between the two. Those get mixed up sometimes. Okay, a frame of reference, I'm going to define it here first. Frame of reference. Frame of reference is the baseline. Baseline. It's typically what's not moving, which is hard to define. And we'll just kind of go through a little thought experiment here, right? What are we going to choose as a frame of reference? Right? What are we going to what are we going to make our baseline, right? So this is an airplane. I used to draw an airplane. Now I've now extracted this, and say I'm on that airplane. I'm on this airplane, and I'm playing frisbee with my son. One of my sons. We're throwing a frisbee back and forth on that airplane, right? What do I choose as my frame of reference, right? If I'm on the airplane and I'm traveling through the air, I would choose the frame of reference being the airplane, right? Like if I'm trying to judge that frisbee or baseball coming at me, I would like to take as my frame of reference the base of the airplane, because that ball will be coming at me at 20 miles, or the frisbee will coming at me 20 miles per hour, relative to the plane, which we're both on and we're traveling through. And so really what I care about at that moment is that it's coming at me at 20 miles an hour. How fast is it really going? Well, 520 miles an hour, right? But I happen to be traveling 500 an hour, so then you get the point, right? It's like it's traveling at 500. If I was down here, if I was on the Earth, I'm going to draw the Earth as being round. Okay, the Earth is round, it's not flat. I gotta throw that out. I every once in a while. I know a couple flat earthers. But in the class we were studying physics. And later on we're getting into orbital mechanics. If you're not believing that the Earth is round, you might need to come talk to me a little bit. This might not be the best class for you. It's cool. When you get into orbital mechanics, that shit's cool. I think that's super cool. It's pretty neat. Okay, but if I'm observing that here, right? If I'm observing that from the Earth right here, and I'm looking up at that thing's traveling at 520 miles an hour. If I'm on the plane, it's traveling at 20. So what do we pick as a frame of reference? And we'll talk about this a lot more later too, but what do I pick as my frame of reference? Do I pick the surface of the Earth? Because that's not moving, right? Shit, that's moving too, right? So then do I pick the center of the Earth, because we're rotating, right? Because the Earth's rotating. So I'll pick the center of the Earth as being our frame of reference. No, that's moving too, right? Because that's circling around the sun, right? So I'll pick I'll pick the center of the sun as being the frame of reference. No, that thing's moving too, right? It's circling around the center of the Milky Way galaxy. So I'll pick the center of the Milky Way galaxy. No, that's expanding, accelerating. We're all expanding there. It gets deep, right? But that being said, for this class, mostly we will be considering the surface of the Earth as being not flat. Almost said flat. Well, there's some instances of projectile motion we do assume the Earth's flat, but we'll be assuming that the surface of the Earth is not moving, right? Certain problems, like quickly, if you're doing intercontinental ballistics, you do have to consider the fact that the Earth is actually rotating. And so you have to pick a different frame of reference. But most of the problems in this class, our frame of reference will be just the surface of the Earth. The surface of the Earth is not moving in that case. So that's just introducing this idea of a frame of reference. A coordinate system is a specific set of coordinates within a reference frame. Okay. In this class, we're going to deal with Cartesian. That's usually our favorite. But we're also going to do polar and normal tangent. We use a couple different coordinate systems, but they live inside the reference frame. First, you got to define the reference frame, and then you have to define the coordinate system. Okay, any questions so far? Right now we're just kind of like, velocity is the derivative of position, acceleration is the derivative of velocity, right? These problems that we start out solving involve, we'll do some examples at the end here, but they all kind of involve, all right, here, your car is accelerating at this rate after how many seconds, how far has it traveled, or what is its velocity after a certain amount of time, right? Or the opposite, it starts out with position. Here's a position here and here's a position there. What was the velocity in between the two? It's all associated with, moving around between acceleration, velocities, and positions, or positions, velocities, accelerations, going one direction or the other. They're all kind of associated with that. Where it gets difficult is there's going to be different types of problems. There's acceleration's function of time, acceleration constant, acceleration function of velocity, acceleration function of position. Those types of problems kind of convolute things a little bit. What we start out with, just to kind of make things as easy as possible, is we start out with 1D motion, just something traveling in a straight path. Okay, and then we're going to move on to 2D and 3D motion, which just happens to be multiple 1D problems. So we just start out with 1D problem, we'll understand that, and then we'll do 2D and 3D problems, which are just multiple 1D problems, and then it makes our lives a little bit easier. Okay, so then again, the book starts out with this one. This is the same path that they take. They start at 1D motion. There's no vectors. We're going to drop the bars here because they're not vectors anymore because they're only 1D problems. We're going to do 2D and 3D problems. Problems are just multiple 1D problems. We're just going to learn stuff in 1D, and then we'll take it on into 2D. Okay, so here it is, our position, going from one thing to the other, that position R. The book calls the position when we're dealing with just 2D as just S. Right? When it's just a 1D problem, that just becomes S. We're going to drop the bar on top of it and call it S. Okay, so then when we define velocity, that velocity is just going to be ds dt, the derivative of s with respect to time. We call that s dot. Right? If you had a plot of s versus time, then velocity is that slope. We call that v over 1. And then acceleration is dv dt, which is just v dot, which is equal to s double dot. And if we had a plot of velocity, acceleration again would be the slope of this, a over 1. And again, the book kind of goes through these exact same steps. We've kind of related now velocity, acceleration, and position added this new variable s, right? And this is what I was talking about before, where these problems get a little difficult. And this actually, right away now, we're starting to diverge away from physics, because I don't think physics does all these. I think physics typically does acceleration of function of time. They don't do acceleration function of velocity or acceleration function of position. Okay, so again, back to my statement earlier about when we do these problems, we really try to make them. I'm going to try to give you a procedure to follow, right? A very like a cookbook, if you will. Like a lot of times they say don't do cookbook engineering, where you're like, in dynamics I teach cookbook engineering. We're gonna identify the problem. We're gonna say, oh, it's this type of problem. We're gonna go to that type of problem, and we're gonna see how to solve it. You don't. Where people run into problems with this is they always assume that it's acceleration of function of time, even though it's not. And they try to solve it as if it's acceleration of function of time, and they do it the wrong way. Okay, so you have to identify. So when you go to solve this, you're going to say, what kind of problems do I have? Do I acceleration function time, constant, acceleration function velocity, or acceleration function position? And then given those, I'm going to now give you how to solve each one of those problems. Okay. Before we get started, well, let's go. Acceleration of function of time. What is it something that is acceleration of function of time? A car speeding up, perfect example, right? You step on the gas, right? And it starts accelerating. Is it a constant acceleration? No, right? It takes a while for the RPMs to get up and stuff like that. So it takes a while. That force, your thrust behind you, is changing with time. Starts out at one speed, and then it's at one acceleration, one amount of force, and then it accelerates from there. And that acceleration changes with time as it's going up and it's changing gears. Like that's actually, it's accelerating, or changes gears, and accelerates, and changes gears and accelerates. Right? That's acceleration of function of time. It's a perfect example, right? What about a constant acceleration? Yeah, we pretend it is, right? We pretend it's constant. Is it constant? It's not, right? The further you go, right, it's inversely related to the distance between two objects. So when you're dealing, for all of our problems, we're going to assume it's constant, right? Because we're dealing with the surface of the Earth is not moving, and then we'll assume that also gravity is constant. When we do orbital mechanics, now we're talking about getting distance away. Then we have to take into consideration that gravity does change with respect to distance. Okay, so that's exactly right. That's the best one. Constant acceleration will be our pretend gravity. What about acceleration of function of velocity? When would acceleration change with velocity?
Ball rolling across the floor. Is it friction?
I can see that. A better one, not that that's a bad one, but a better one.
Air resistance.
What's that?
Air resistance.
Air resistance. That one's a real, because a ball thing, I think friction would probably kind of be constant independent of velocity. But air resistance, drag, that absolutely, right? The slower you move, the less drag it is. The faster you move, the more drag it is. And so your acceleration will be, the amount of force you're putting into your car as you're driving your car, the more air resistance you get, the more you have to put in, the more you have to accelerate against that. Or a terminal, we jump off of a building, that air resistance, the faster you go, the air resistance is higher. And so your acceleration down will be a function of your velocity. That's another example. What about acceleration of function of position? Real gravity, yeah, not pretend gravity. That's right. Real gravity is acceleration function position. There's another one. There's another one too. That's simpler than, well, not simpler than gravity, but different. Well, something where the force changes with respect to position, because that's it, right? It's all related to force, right? Forces and accelerations are tied to each other. What's something where force changes when you change position? A spring, right? So if you have something involving a spring, that's going to be acceleration of function of position, right? Because the more you compress the spring, the more force you have. The more force you have, the more acceleration you have. The less it's collapsed, or the less it's deformed, then the lesser the force, which means lesser the acceleration. Okay. So we're going to go through each of these problems and how to solve them. We'll write down those things. So acceleration of function of time. We talked about this just a second ago. Car accelerating. Right, force is changing with time. Okay, so what we do is we start out with, right, acceleration of function of time, a of t is equal to dv dt. And I mentioned this before. It's all about kind of moving around in this space, right, of velocities and acceleration. So I'm going to go from acceleration to velocity, right? That's the first thing I want to do. So acceleration is just dv dt. And what I do is I kind of move that, some shorthand we'll introduce here in a second. We'll go back to some calculus stuff here. I'm going to put the dt over with a of t. So a of t dt is equal to dv. That's all I did is I just took that dt, I took this little dt right here, and I moved it over to the a of t. So it's a of t dt is equal to dv. And at this point, what I do is I integrate both sides. Integrate. I'm taking this one from t naught to t, and this one from v naught to v. I'll make this. I'll make a statement right now. If you tried to, like, if you were like a fundamental math person, like if I was a math teacher, I would run up and I'd slap my hand right now, because you can't theoretic or based on math rules, I can't make this t and that t and integrate with respect to t. I can't put my bounds on my integral the same thing as my of what I'm integrating with respect to. That's breaking a rule. I'm a rebel, and I'm going to break that rule anyway. Just it makes the writing this stuff a little bit faster. Technically, that should be a dummy variable. You'd have to have dummy variables. You can't call it the same thing. And if you tried putting that in your calculator, the calculator would say, nope, you can't do that. But we're going to do it because we're rebels. Okay, it just makes our lives a little bit easier. So I'm going to integrate the bounds of these things from t naught to t. So the initial time to the future time, and then from the initial velocity to the future velocity, okay? And the left-hand side, I don't know what, I haven't said what, we don't know what that equation is right now, so I can't simplify this anymore, but I can simplify this. If I just take the integral of dv, this just becomes v minus v naught. Right? If I just integrate dv, because that's what I'm doing, I'm just integrating dv, that's just gonna be the bounds v minus v naught. It's just the initial bound minus the other one. So it just becomes that. And so what I'm after is velocity. I mentioned that before. So what I do is I just solve for that velocity. I'm after that. So I just put this v naught over on this side over here. Okay? And then that leads us to this equation that I've pre-written for you here. Okay. So if I want velocity, if I have a function, acceleration, a function of time, and I want to go from acceleration to velocity, there's your equation right there. Okay? I just take v of t is just v naught plus the integral of a of t dt from t naught to t. Right? And that's as simple as I can get it right now, because what a of t is varies. Right? It's just part of the problem statement what that acceleration is. Right now, that's as far as we can go. Okay. If you want to do velocity now, you come down, or you go from velocity to position. That's our next step. We do the same thing, the same type of procedure here. We say v of t is equal to ds dt. Same thing. I put the dt over with the v of t dt is equal to ds. I integrate that from t naught to t, and this guy from s naught to s. Again, I can't integrate the left-hand side, but I can integrate the right-hand side. That just becomes s minus s naught. And then you solve for that s. So you just put the s naught on the other side, and what it gives you is this. And this is what you should remember from physics, right? This whole idea of taking if I want velocity, I just integrate the acceleration and add on the initial velocity. If I want position, I integrate I integrate the acceleration that gives me velocity. And then if I want position, I then integrate the velocity and add on the initial position, and I'm there. Okay. Let's review. That process only works when it's acceleration of function of time. If you have acceleration of function of position or velocity, that doesn't work. And so time and time again, we'll have students come in to the help center or to my office and be like, I can't get this right, I get the wrong answer. And it's because of that. It's because you're assuming this. It's the A team coming in, right? 8 for you, right? Exactly right. All right, that's a good stopping point. Okay, so then the next time we'll do acceleration, a constant acceleration, which is actually the same as acceleration of function of time. It just is not moving, okay? So we'll lay those things out, and then we'll do acceleration function of position and acceleration function of velocity. And then after doing that, we'll do some example problems. Any questions about that stuff? So I'll probably assign a homework today. It'll be smaller just because we're not going to get through a lot but by next week. Any questions? We're good? All right, well, let our TA people start. We got Flynn, Dawson, Jamie.
Hi, everyone. Some of you I got to know last semester, which was very fun. And
Whether you like it or not, she's back again.
back
so.
again, but in a much more, you don't get to deal with me as much. I'm sorry. I'm going to turn you over to these two very competent gentlemen. So I still manage the Learning Center. I hope you used it last year for statics, and I hope it was helpful. If it wasn't helpful, please tell me why so that I can try to change that and make it helpful to you. Like that feedback, it's in the same place, Roberts 317. It's not bigger, but it feels bigger, so that's exciting.
Optical illusion.
Yeah. So we'll put up the schedule. It'll open on Monday. So you'll probably be there for mechanics and materials on Monday, and then vote the schedule. It'll open on Monday. We'll post a schedule. Dawson and Jamie and Thomas, who you worked with in statics, I'm sure some if you went there, he'll be there as well to help you throughout the week, focusing on the Thursday, Friday push that you'll likely be in. We're also doing recitations for this class now too on Wednesday evenings. Jamie will be leading them and Dawson will be there to, sorry, potential spam calling. So Jamie will be leading those Wednesday 5:10 to 7 in Roberts 312, the same room that we were in last semester. I think those will be really good for you all. It should be interactive. So you'll be here with Dr. Barry. He's going to tell you a bunch of stuff. He's going to give you example problems, send you on your way with a bunch of homework. The reason why we chose Wednesday is you'll have learned everything you need to know by that point to do your homework for Friday. So these two are going to be ready to reinforce those concepts, give you practice, help you along the way, and then get you ready to understand this beautiful subject.
It's beautiful.
It is a beautiful subject, but it is a very difficult subject, and that's why you have so many resources coming at
Right.
you. You have Dr. Barry, who's amazing. You have,
true.
You have the Learning Center. You have recitation sections. You have 3 awesome TAs. So you have a lot of resources. You can come and tell me if something's wrong. Use me as a resource too. So so I'm gonna let Dawson and Jamie tell you a little bit about themselves, and you should get to know them better.
What about you?
Well, me,
Who you are, where you're from, something interesting about yourself.
Well, I'm Flynn. I'm from Minnesota. Something interesting about myself is I started college here in 2005.
Predates
Which
me.
is actually before Dr. Barry started
right.
working here. So I've been here a while.